Hello everyone, welcome to the next lecture, next part of a lecture, lecture number 12, in which we are going to look at another interesting topic, probably the last topic of this chapter, before we go to chapter number 13 and talk about model circuits and Laplace transform in much more detail. Okay, anyhow, the last topic of the Laplace transform is something that is called as the initial and final value theorems. So in this part, we are going to derive those theorems, and in the next part, we are going to do an example problem with the circuit as well. Okay. So what are the initial and the final value theorems? So the idea is that again, you are starting with the circuit, you got this differential integral equations, you convert that into a Laplace transform, f of s function, right? Before you inverse transform it, right, you can do in the s domain as well with s f of s functions, you can figure it out what is going to be the time domain responses at 0 and at infinity, what their initial values are, what their final values are in the time domain by looking at the function in the s domain. So this is what we are practically going to do. We're going to find out the behaviors of f of t at 0 and infinity while playing around in f of s. But in this part of the lecture, I'm going to drive those drive those things. Here's the initial value theorem, which means that as t approaches to 0 positive in the time domain function, so the initial value of f of t, or you can also call it at f of 0 positive, right? Your initial value that we looked at in the circuit analysis, right? What is the initial stored in the capacitor? What is the initial energy stored in the inductor, for example? What it looks like in the s domain. In the s domain, we can find it out by multiplying f of s with s and then taking a limit as approaches to infinity. I'm going to derive this in a second, and then we're also going to do an example problem to make sense of it. And the final values theorem states that, let's say the final value of the time domain function, right? This is the final value of the time domain function, f of t, and limit t approaches to infinity. This final value of the time domain function, in the s domain, we can figure it out by multiplying f of s with s and then taking a limit as approaches to 0. So let's, before we actually derive it, a couple of other important points, and then we're going to do the derivation. There's an interesting assumptions for both initial value theorem and the final value theorem. The initial value theorem, since it is about the initial values of those energy stored elements, for example, in case of a circuit analysis, but the assumption of this kind of a mathematical equation over here is that this equation is valid as long as there is no impulse at 0, or that you should have some sort of a finite value at 0, or there's a finite value exists at 0. And similarly, for the final value function, assumes that you have all the poles are in the left plane, and this is the physical intuition that we were talking about earlier as well, right? All the poles lie in the left half of the s-plane, right? Left half of the s-plane, right? All over here. This is going to make sure that you have a stable response of the system, right? Okay, that all the natural modes will die out as t approaches to infinity. Yeah, they lie in the left half plane and the system is stable. Okay, so with these assumptions, let's start with proving those initial and the final value theorem. So here's again the initial value theorem, which is limit t approaches to 0 positive f of t should be equals to limit s approaches to infinity s of f of s. So in order to prove them, I'm going to kind of start with taking a Laplace transform of a derivative of a function, right? So if I'm going to take a Laplace transform of a derivative of a function, I'm going to get, and I have kind of, we had a whole lecture in trying to derive this thing as well. The answer is s of f of s minus f of 0 negative. But I can also write in actually in the overall regular integral, which is 0 minus to infinity, derivative of f of t divided by dt times e raised to power minus st times dt. Okay, great, right? So this is, I started with again taking a Laplace transform of our derivative of a function. Okay, now let's take limit s approaches to infinity both sides. Okay, so if I'm going to take a limit s approaches to infinity, on the left hand side, I'm going to get s of f of s minus f of 0 negative equals limit s approaches to infinity, I'm going to get 0 negative to infinity df over dt e raised to power minus st times dt. Okay, so I just started with the derivative of function, expanded it out, and took limit on both sides. Now let's solve for the right hand side. Okay, I'm going to solve for this first. Okay, so this is kind of interesting. I can expand this integral more. For example, let me expand this integral s approaches to infinity. I'm going to expand this from 0 negative to 0 positive df over dt e raised to power minus st dt, right? And then plus 0 positive to infinity df over dt e raised to power minus st times dt, right? So I started with the right hand side and I expanded the right hand side into these two parts. Why I did that is going to become very clear shortly, because essentially if you look at this part is right, this part is 0 positive to infinity, right? So since my limit is also approaching s is approaching to infinity, when s is going to approach to infinity, it is going to make e raised to power minus st to 0. When e raised to power minus st is going to approach 0, it's going to get multiplied with whatever the derivative is. It should make the whole thing 0, right? So this entire thing is going to come out to be 0. Now let's look at this part now, right? What is going to happen in this part is, first, this integral is very limited to centered around minus 0 negative to 0 positive, is literally at kind of 0. So this can further be reduced to 0 negative to 0 positive df over dt e raised to power minus 0, right, which comes out to be 1 times dt. And again, you can take a limit as approaches to infinity. So again, my right hand side will be reduced to limit as approaches to infinity 0 negative to 0 positive df over dt times dt. Okay, this is a simple identity and I can solve it as, again, you get f of 0 positive minus f of 0 negative, right? This is f. So this is right hand side. Let's play with the left hand side a little bit as well. So your left hand side was limit s approaches to infinity, right? This thing times s of f of s minus f of 0 negative. Again, this has f of s. This has a s multiple over here, but this is a constant, so I can take this outside the limit and I can rewrite this as limit s approaches to infinity s of f of s minus f of 0 negative. Now I'm going to combine left hand side equation. I'm going to equate left hand side with the right hand side, right? So left hand side equals right hand side. So the left hand side is, again, limit s approaches to infinity s of f of s minus, right? So let's do this. F of 0 negative equals f of 0 positive minus f of 0 negative. Okay. So interestingly, f of 0 negative will be cancelled out and I will be left with limit s approaches to infinity s of f of s equals f of 0 positive. Okay, so what is this f of 0 positive, right? This is the value of the function at 0 positive, right? So I can easily write this thing down as t approaches to 0 positive f of t, right? And if I'm going to replace it back over here, limit s approaches to infinity s f of s is limit t approaches to 0 positive f of t. And this is exactly my initial value theorem, right? So initial value theorem starts with over here. We can see that limit t approaches to 0 positive f of t equals to limit s approaches to infinity s of f of s. So this is how we can prove the initial value theorem as well. Very quickly, I'm going to do a final value theorem, and then we're going to do an example problem to make sense of why this was kind of needed. Okay, again, the final value theorem is the final value in the time domain, right? The final value of f of t in the time domain is equals to when you apply limit s approaches to 0 on s of f of s. So this is how you can calculate the final value in the time domain, in the frequency domain, or in the s domain. I'm going to start with exactly the same way. The first step is the same. I'm going to take a Laplace transform of a derivative of a function. So the first step is going to look exactly the same thing, right? So this is, we know that expansion, and then we can gonna do this integral as well, 0 positive to infinity, and d f of t by dt e raised to power minus st times dt. Okay, nice. So we ended up getting this thing, and then I'm gonna apply on both sides limit s approaches to 0, right? Apply limit s approaches to 0 both sides. So I will get limit s approaches to 0 s of f of s minus f of 0 negative, limit s approaches to 0, 0 positive to infinity, df over dt e raised to power minus st times dt. Okay, so this is interesting. So we are again going to start with right hand side, right? So let's start with the right hand side, where I am interested in finding the limit s approaches to infinity, s approaches to 0 here on 0 positive to infinity, df over dt e raised to power minus st times dt. Okay, now I am going to do something very similar that we have done over here, right? Where I mentioned that when we approach s approaches to infinity, so we approach s approaches to infinity over here. Sorry, coming back here. Okay, so over here we have a limit s approaches to 0, 0 positive to infinity, and df over dt e raised to minus st, this thing. So what we are going to do is, since our s is approaching to 0, I can do e raised to power minus st, can potentially e raised to power minus 0, it can become 1, and then I can further simplify it as limit s approaches to 0 is integral of 0 positive to infinity df over dt times dt, right? And practically, since this was the only term with an s, and when we approach it to 0, this is practically going to become 1, right? So why I didn't consider the whole integral, because this is a limit that we are kind of the final values that we are looking at. These are final value theorems, right? So once I'm going to apply the limit s approaches to 0, so I can evaluate this integral at s approaches to 0. So that is why e raised to minus st, e raised to minus 0 became 1, and I am left over with this integral. So practically, since I'm left over with this thing, this is equals to just 0 positive to infinity df over dt times dt, because the limit, there is no s variable to apply the limit now, right? So if I'm left with over here, this is a simple identity, right? And I can further do another interesting thing to this, right? So let's say I have 0 positive to infinity. Sorry, why is it 0 positive here? Huh. Okay, sorry. I made a mistake from the very first step over here, and the mistake was just a limit of integration, right? We know that in the Laplace transform, it's a unilateral transform. I don't know why I was writing positive. It should be 0 negative, right? So this thing should be 0 negative. This thing should be 0 negative. This thing should be 0 negative. This thing should be 0 negative, right? Because this is a convention that we have for the whole chapter for the past 2 weeks. In the unilateral transforms, we are including the if there's any discontinuity, we are including that as well. So that is why we are starting with the 0 negative. Okay, so again, my integral of 0 negative to infinity df over dt times dt, I can rewrite it as interesting thing that I'm going to do is I'm going to approach this as t approaches to infinity, 0 negative to t, df over dy times dy. Okay, so I ended up doing two things here, right? First, my limits of integration were from 0 negative, which is 0 negative over here, so sure. But my upper limit of integration was infinity, right? And again, I am taking an integral integration with respect to time t. So the very first thing that I ended up doing was I can rewrite this integral, which is going from 0 negative to all the way to infinity, right? I can rewrite the integral 0 negative going all the way to infinity to 0 negative all the way to t when t approaches to infinity. So essentially, this is what I ended up doing. Another important thing, since I ended up doing that, another convention that we have been following is that if your variables, if your limits of integral, right, will have the same variable, then we change the variable of integration. So we change the variable of the integration again to avoid the confusion, and that is why we got this dy. But eventually, if whatever the function you're going to solve, you're going to get back time t. Okay, so you are left with this function now, limit t approaches to infinity, 0 negative to t df over dy times dy. Again, as you can see that this is going to come out to be limit t approaches to infinity, and if you will solve for this integral, this is going to come out to be f of t minus f of 0 negative. Okay, nice. Now I can combine left and right hand side. Combine left hand side and right hand side. So my left hand side was this, limit s approaches to 0, s of f of s minus f of 0 negative, and over here limit t approaches to infinity, f of t minus f of 0 negative. Again, I can take limit s approaches to 0, s of f of s here, and I can take this f of 0 negative out. And over here, t approaches to infinity, f of t, I can take f of 0 negative out of the limit, right? So this will be cancelled out. And again, I will be left with limit t approaches to infinity, f of t is limit s approaches to 0, sf of s. So this is your final value theorem. We're going to apply this final value and the initial value theorem in the next slide, in the next part of this lecture, and we're going to do a circuit problem. But again, this is the derivation, and again, the final value theorem is only useful, right, if f of infinity exists. And in order to make sure that f of infinity exists, we said that the poles should be on the left side of S plane. Okay, so again in this lecture, let me give a one quick summary, right? So we started with talking about the initial and the final value theorems and the need of it, because imagine that our time domain equations, differential equations, have been converted into a function f of s. But before we do an inverse transform, we are interested in, you can even call it a sanity check. We are interested in making sure that that makes sense. So we are interested in finding the value of the time domain functions at the initial values and the final values. But we have f of s available. So how we can do that? We develop these functions, the initial and the final value of theorems. And we said that, okay, our assumptions is that initial value theorem is only practical or applicable when you have a finite value at 0. And the final value theorem is practical only if your poles lies in as on the left hand side as equals minus something, right? So that you have a stability in the system and your system decays. So then we did the proof of the initial value theorem and the final value theorem. The good thing about both of the proofs are that they start with finding the Laplace transform of a derivative of a function, right? And then we kind of took the left hand side and the right hand side and did the whole thing. And similarly, we did a final value theorem proof. We started with the Laplace transform of our derivative of function. I had this typo where I started this with a 0 positive. Again, we have been doing Laplace transform. We always start with a 0 negative. So this is how you can find out the whole thing and prove the initial and the final value theorems, and that should make sense. Okay, so with that, I'm going to finish this lecture. In the next part, we are going to do a circuit problem for the same thing. All right, thank you so much. Have a great rest of the day. Thanks, bye.